Hello, this is Dr. Brown. In this video, we're going to talk about the real zeros of polynomials. This slide gives us an idea of some of the topics we're going to cover. If you see a red X by it, we're not going to cover that topic. So we're not going to cover the remainder and factor theorems, which are hardly or rarely ever used in helping okay. Let's go ahead and we're going to cut out this first part. Hello, this is Dr. Brown. In this video, we're going to cover the real zeros of polynomials. This slide gives us an idea of some of the topics we're going to cover. Because I have an X by it, a red X by it, we're not going to use a remainder theorem, but we are going to use a very important theorem called the factor theorem. We're not going to cover Descartes' rule of signs, which at one time was used to help determine the number of negative and real zeros of polynomials. But with modern real fast calculators, graphical calculators, nobody really uses this to analyze a polynomial function. We're also not going, we may cover briefly, talk about the rational zeros theorem, but really not going to use it to list the potential rational zeros of a polynomial, because we can use our calculator to find all of them very quickly. We are going to spend time looking into how to find the real zeros of a polynomial function. We then will obviously be solving polynomial equations, and we will not look very much into the use of the theorem for bounds on zeros, but we will look into the intermediate value theorem. Now, a very important theorem that you really need to understand consists of two separate statements. If you have a point C, x equals C, if f of c equals 0, then you know that x minus c is a factor of the function f of x. Now, conversely, if x minus c is a factor of f of x, then you know f of c equals 0. Here's an example using the factor theorem. We have the function f of x shown here, and we want to use a factor theorem to determine whether the function has a factor x minus 1. Well, if we set x minus 1 equals 0, x equal 1 should be a 0. So let's check it out. F of 1 equals 2 times 1 cubed minus 1 squared plus 2 times 1 minus 3, and this equals 2 minus 1 plus 2 minus 3 equals 0. So it checks. It is a factor. Now let's check the other one. Trying to erase what I have here so far. if x plus 2 is a factor, then x equal minus 2 must be a 0. So we will plug in f of minus 2 equals 2 times minus 2 cubed minus minus 2 squared plus 2 times minus 2 minus 3 equals minus 16 minus 4 minus 4 minus 3 equal minus 27, which obviously is not equal to 0. So x plus 2 is not a factor. Now, another theorem. The number of real zeros. A polynomial function cannot have more real zeros than its degree. So if we had f of x equal x to the 4th plus 3x cubed minus x squared plus 20x minus 40, 4 is the maximum number of real zeros. And it may not have 4 zeros. It could have 4 real, 2 real, 2 imaginary, and we will learn a little bit more just a little bit later in this presentation that if there are complex zeros, they come in complex conjugate pairs. Just to sort of get you ready for that, if x equal 1 minus I is a 0, then 1 plus I is a 0. Now, we're not going to use the rational zero theorem, but it is one that I actually used back when I had no graphing calculator back at Georgia Tech a long time ago. And at that time, you had to look at your function of x of nth order, and you had to look at the factors of a sub n and the factors of a0, and then you calculated P over Q, and would check if these are factors, if this was a 0 of the function. So you can see that the various P over Q's could be greatly more than the degree. And so you would be checking lots and lots of zeros by trial and error. And it took a lot of time. Now we use a calculator to do this. So now, find the real zeros of a polynomial function. Here's an example how to find the real zeros of a polynomial. What I want you to do is, and then write the function in factored form. So here is the graph of the polynomial, and I'm going to go ahead and bring up the graph with the calculator just so you understand how to calculate this. So let's graph the equation. Y equal 2x cubed plus 11x squared minus 7x minus 6. Zoom to the standard window. And notice we see 3 zeros, which is all the equation could have. But let's change the window so that we can pick up the maximum. And I'm going to try x min of minus 7, x max plus 5, y minimum, we'll keep that at minus 10 and go to like plus 80 for the maximum. And if you don't quite get it, you can try it again. But anyway, graphing it, we see that we now have a graph of the equation, and we can see that the zeros are minus 6, minus 1/2, and plus 1. Now you can put these in your calculator just to make sure. That means then that the factor for f of x would be x plus 6, x plus 1/2, because that would give a 0 of x equal minus 1/2, and then x minus 1. Now notice, in order for all this to multiply out to 2x cubed, we need to put a 2 in front of this and multiply the 2 times the factor x plus 2, and this would simplify to x plus 6, 2x plus 1, and x minus 1. And so these factors multiplied out would give us the original equation. Now, let's find the real zeros of a polynomial function. It's a fifth order given here. And I'm going to go ahead this time and we're going to graph the equation. Let's clear the previous graph out and put x to the 5th minus 7x to the 4th plus 19x cubed minus 37x squared plus 60x minus 36. Now always put this in your calculator very carefully and check it. And then to zoom to the standard window, we may have to change the window a little bit. But notice we pretty much have the graph completed, and see 1, 0 at x equal 1 and a 0 at x equal 3, which, because it just touches, must be a repeated 0. So let's change the window from x min equals 0 to x max equal 4, and change this a little bit from like minus, well, let's just leave it minus 10 to plus 10. So here we see the zeros. You see 1 at x equal 1, 1 at x equal 3, and this is a repeated 0. And we see no other zeros, so the other two must be complex, which we will address in a later lecture. So now let's look at x minus 1 times x minus 3 squared, which must be a factor of the original equation. And if we multiply this out, we get x minus 1 times x squared minus 6x plus 9. And multiplying the entire thing out, we get x cubed minus 6x squared plus 9x then multiplying the 1 by everything, we get minus x squared plus 6x minus 9. And notice this becomes x cubed. Adding up your x squares, you get minus 7x squared. Plus 15x minus 9. So now I want to use long division to divide x cubed minus 7x squared plus 15x minus 9 and divide that into the original equation. And I'm going to give myself a little room here. And let's do the long division. X cubed goes into x to the 5th, x squared times. Multiplying, we get x to the 5th minus 7x to the 4th plus 15x squared minus 9x squared. And now we draw a line and we subtract x to the 5th minus x to the 5th is 0, minus 7x to the 4th minus x to the 4th is 0. 19x cubed minus 15x cubed is 4x cubed. minus 37x squared minus 9x squared is minus 28x squared. Bring down the 60x and the minus 36. And now go x cubed goes into 4x cubed 4 times. And now multiply 4 times the divisor and you get 4x cubed minus 28x squared plus 60x minus 36. And notice you subtract and you get 0. And indeed then the factor x minus 1 and x minus 3 squared those are factors of the original equation. And since it divided in to the original and gave us x squared plus 4 with no remainder, we know that the other factor is x squared plus 4. So there we have it in factored form. Now we want to solve polynomial equations. This is going to be easy because this equation happens to be the original equation that we just looked at. Find the real solution to this equation, and we'd find that since this is the same equation as we just looked at, the zeros are 1 and 3, because looking at the factored form, the factors are x minus 1, x minus 3, and we see the zeros clearly on our calculator. One other theorem, this will sort of become apparent the more you work these problems. The theorem is that every polynomial function with real coefficients can be uniquely factored into a product of linear factors and or irreducible quadratic factors. So you may end up seeing f of x could be factored into, say, x minus c1, x minus c2, that could be a double 0, x minus c3, and then maybe x squared plus c4 squared, x squared plus, say, c5 squared. But you would have a combination of linear factors, x minus 1, like x minus c1, and quadratic factors. Now, here's a theorem that if you think about it a little bit, it's probably obvious. It says a polynomial function with real coefficients of odd degree has at least one real zero. Well, why is this so? Well, if f of x is of odd degree, n is odd, then no matter what the function looks like in between, it's got to be up on the right and down on the left. So if it starts down here and ends up here because it's an odd function, or if it's over here and down here, so if it's up on the left and down at the right, we got two possibilities. Because a polynomial is always connected if you start on the downside and go to the upside, it has to cross the x-axis at least once. It could do it more, but it's got to cross at least once. By the same token, if it's up on the left and down on the right, and it's a continuous function, it's got to go through at least once. So anytime you see a polynomial of odd degree, it's got to have at least one real zero. It could have more than one, but it's got to have at least one. Use the intermediate value theorem. We're going to cover this very quickly. This is pretty much common sense. The intermediate value theorem says that if f is a polynomial function, and if a is less than b, and if f of a and f of b are of opposite signs, there is at least one real zero of f between a and b. Well, it's sort of like the odd polynomial we just looked at. If a function at a is below the x-axis and the value of the function at b is above the x-axis, and it's a polynomial, then it's got to be connected. It couldn't have any breaks. So there's no way for the function to get from down here to up here without crossing the x-axis. So it's got to have at least one zero. And we're asked to use the intermediate value theorem to locate a real zero of this function, x to the fifth minus x cubed minus 1, to show that it has a zero between 1 and 2. So what you do, take f of 1 is equal to 1 to the fifth minus 1 cubed minus 1 equals 1 minus 2 equal minus 1. And f of 2 is 2 to the fifth minus 2 cubed minus 1 equals 32 minus 8 minus 1 equal 23. So this is below and this is above. So it must cross the x-axis between 1 and 2. Here, and I'll let you suggest that you do this yourself as you watch the video, put in the equation x to the fifth minus x cubed minus 1. And indeed, if you draw the graph, you'll see that it crosses the x-axis between 1 and 2. And that is the lesson for today.